Okay, as promised, in this video we're going to construct the Grothendieck spectral sequence. So let's remember what that spectral sequence looks like. Well, for our Grothendieck spectral sequence, we start with some abelian categories and some left exact functors between them. Oh, my poor cat is crying outside. She's so over me working. Okay, so these are left exact functors between abelian categories. And remember that we said that A and B should have enough projectives. So we're finally going to see how these hypotheses come into play. We also had that F takes injective objects to G acyclic objects. And then what is our spectral sequence? Well, it's a first quadrant spectral sequence whose E2 page is the right derived functors of G applied to the right derived functors of F applied to some object A. And this converges to the right derived functors of the composition. And then we apply it to A. Okay, so this is going to be a proof sketch. Well, really, it's a sketch in part because I didn't prove any of the lemmas that led up to this from the last video. But also, we, of course, still have some convergence issues to deal with, and I promise those are coming soon. But let's construct this spectral sequence using a double complex. So what we want to do is find a good double complex. And then remember there are two spectral sequences, so somehow we want to play those two off each other to find out about this spectral sequence. So we'll see how that goes. Okay, so how do we start this off? Well, we take our object A in our abelian category A, and that had enough injectives, so we can take an injective resolution. Oh, she's so sad. I don't know if you guys can hear that. My poor cat. Okay, now we're going to take a proper injective resolution. So remember, that's a double complex of a bunch of injective resolutions for some cochain complex. And what cochain complex will we use? Let's do this for our left exact functor F applied to, sorry, not A, but applied to this injective resolution. Okay, so of course we need to have enough injectives there, and this F of I lands in B, and we had enough injectives, so great, we're going to be able to do that using, of course, these lemmas from the previous video, including the horseshoe lemma along the way. So what does this look like? Well, we get this big double complex. So at the bottom, we've got F applied to I0, F applied to I1, F applied to I2, and so on. Okay, and then I want to take an injective resolution of each of those things. So maybe I'll call it J00, there's some J01, and so on. So this whole column is an injective resolution of that first thing. I should have an injective resolution of the second thing. And the third, and so on, of course. I'll just draw this little bit of it, mostly because it'll help to have it to refer back to. Okay, but remember that a proper injective resolution is not just an injective resolution of each of the pieces. We've also got these horizontal maps, making this a double complex. Okay, and what makes this proper? Well, okay, so the columns are injective resolutions. That's just what makes it an injective resolution of a complex. And what makes it proper is that these play well with those double complexes B, Z, and H, right? So the co-boundaries, the co-cycles, and the cohomology. Okay, so when I restrict to the co-boundaries or the co-cycles, it's still an injective resolution. When I take the cohomology with respect to the horizontal differentials, still an injective resolution of this whole complex. Okay, great. So now this isn't actually the double complex that we want to use, but we're close. So we take this proper injective resolution of F applied to our injective resolution, and then the complex we're really after is we take this double complex, I'll call it J, and apply G. Of course, so far we've only used F and we need G in the picture. So, okay, apply G to what we've got here. And what's that going to look like? Well, I only want to apply it to the J, so I'm going to rip off this bottom row, sort of in the same way that we rip off when we do an injective resolution and we start applying our functors, we rip off that bottom piece. So now I want to rip off that bottom row. I'm just going to apply it to the J stuff. And actually, that makes me think I could probably, oh, it would take so much work. It's probably faster if I just write it again. Sorry, feel free to speed ahead a little bit here. So what do I have? I have G of J 0, 0, G of J 0, 1. If I had been clever, I would have written this all with enough space. And then this would have been faster not to write over again, but here we are. So that's 1, 0, 1, 1. Of course, we've got zeros on the edges, and really zeros forevermore, right? So this is the first quadrant double complex. Then maybe just to do a little bit more, 2, 0, oops, 2, 1, so on. Okay, you get the idea. Okay, so this is the double complex that I want to work with. And now let's compare the two spectral sequences. So I want to think of this as the E0 page and compare those two spectral sequences that cook up the cohomology for the total complex. Maybe let's put in there total complex. Okay, so of this G applied to this double complex. Okay, so there's two different versions, and we could go either way. Let's say that we look at our vertical differential first. So let's say we use dV first. What's that going to look like? Well, I want to use the vertical differential, so maybe it's helpful to sort of go back to our original picture. So, okay, what am I trying to say? I look maybe at this first column, and I'm thinking about those vertical differentials. So what have I done here? I just had this F applied to I0, and I took an injective resolution of it. And so when I compute homology with respect to that differential, then really I'm just computing the, then I apply G. So I rip off that bottom piece, and then I apply G, and so now I'm computing homology with respect to those vertical differentials. But that's exactly how I compute the right-derived functors of G applied to some object, and that object is F of I0. Okay, and then I have the same story in the next column. I'm just computing the right-derived functors of G applied to F of I1. Okay, so hopefully that made sense. Let me see if I can write it down. So at the bottom here, we've got our 0G, the zeroth derived functor of G, applied to F of I0. And then the zeroth right-derived functor of G applied to F, applied to I1. The zeroth right-derived functor of G applied to F of I2, and so on. Okay, so this is like my 0 line. And then right above that, notice I'm still drawing these horizontal arrows because we were using the vertical differential, not the horizontal. So right above that I have the first right-derived functor still applied to f of I 0. That came out weird. Okay, and then same thing here, but for f of I1. Same thing here, but for f of I2, right? And just as I go up, I should be seeing higher and higher right-derived functors of this thing applied to fi0 in the first spot, fi1 in the next spot, and so on. Okay, so this was like at level 1, and these continue. Okay, so these are what my sequences look like on the E1 page. And now I need to remember who does what. Okay, so our F takes injectives to G acyclics. Remember that hypothesis. Okay, so when I look at these higher right-derived functors of G, well, each one of these is applied to F applied to some injective, right? And so all the higher derived functors should disappear. So actually let me cross that out. These higher right-derived functors are all 0. Not in general as functors, but on these particular kinds of objects. Okay, and then, so all we're left with is this stuff in degree 0 here. So, okay, fine, but what is that? Well, also, remember that the 0th derived functor is just the functor, right? x0 was Hom, tor 0 is just tensor. Okay, so what we really have is, so for q equals 0, I just mean like on the p-axis in our first quadrant spectral sequence, we have what? Well, we just have these R0G terms, but those are really just G. So let's write that. This really just looks like G after F of I0, G after F of I1, G after F of I2, and so on. Okay. Now remember that these I's, this was coming from an injective resolution of A, so this just looks like the composition applied to an injective resolution. Okay, so now when we use our horizontal differential, what are we doing? We just took G after F, we applied it to an injective resolution for A, and then we're taking homology. Well, that's exactly how I compute the derived functors for the composition. So this just becomes R0 of GF applied to A. This next one is R1 of GF applied to A. Here this is. So now I'm writing the E2 page. This is R2 of GF applied to A. Right, so this was my E1 page, and I figured out that there was nothing up in these higher degrees. These were all zeros. We just had this stuff concentrated at height 0, and it just looked like GF applied to each of the things in the injective resolution for A. And so when I take homology, I'm exactly doing the right derived functors of those for A. Okay, great. Well, now what do we have? Well, this is all just concentrated in degree 0, right? Or in height 0, q equals 0. So then our spectral sequence collapses. There's no room for differentials, right? All of our differentials after starting on the E2 page already, they change the height. So there's no differentials. And in fact, it's even better than that. There's no extension problems, right? These all landed in different total degrees. So we know an associated graded for the thing that we should be converging to, the homology of the cohomology of the total complex. But even better, we don't have to worry about the associated graded. There's no extension problems. We just know what the answer is. Okay, so this is the end of the story. We know that E infinity, I guess, PQ looks like this. Maybe let me just say we have this rather than write this all again. Come on. Okay. All right, so that was one version. Let me kind of separate here and say, let's now take the other spectral sequence route. So let's instead use our horizontal differentials first, and then our vertical differentials. Okay, I'm going to scroll back to the complex that we're looking at because maybe we don't remember. So what did we do? We took an injective resolution of A, we applied F, we put that on the bottom, and then took a proper injective resolution of all of that, and then applied G to that complex. Okay, so now, well, maybe let me recap. In the last version, we did vertical differentials and saw, oh, we were just computing right-derived functors of G all the way up, and what were they right-derived functors are? They were for F applied to injective, so there weren't any higher ones, and in fact, it was just G applied to those things in degree 0. And then the whole thing collapsed. So now I want to take the horizontal differentials first and consider these, and then go vertically. Okay, so let's think about those horizontal differentials. Well, let's think about those horizontal differentials. Okay, so somehow I always get tripped up with my words here, so let's see if I can get this right. We're going to do the horizontal differentials first, and then the vertical differentials. And notice when we do vertical differentials, we really are still computing right-derived functors of G for the same reason that we were before, right? But what are we computing right-derived functors of G for? Well, when we use the horizontal differentials, we're really taking the right-derived functors for F applied to A. That's really what we have in degree 0 here. So if I ignore this G stuff and forget that for a moment and go back to this complex, down here at the bottom, I take F, I apply it to my injective resolution for A, and then I take homology with respect to the horizontal, and that's going to give me the right-derived functors of F applied to A. Okay, that's not what I have here quite, right? But the whole point of this proper resolution is that it plays well with taking homology. So I can actually think about doing that for this first line. Okay, I take F, apply it to my injective resolution, I take homology, and then if I take the homology of that stuff and apply G to injective resolutions for all of that, I'm going to have the homologies here. So the point is that all plays very well, before I apply G. Okay, let me say that again. I said I was going to get tripped up, and I get tripped up with this. So let me say again, if I go back to this complex, I look at the bottom line and I've got F applied to my injective resolution for A. And if I take homology with respect to that complex, just those horizontal differentials, I'm computing right-derived functors of F. Okay, now what did I do to build out this whole complex? I took injective resolutions of all of those things. But the fact that this is proper says that it plays well with taking injective resolutions of the homology, right? The homology of all of this stuff with respect to the horizontal should be the injective resolution of the homology here. Okay, so then I have this injective resolution of the homologies, and then I apply G, and then I'm doing the right-derived functors for G as I go up to whatever I had. Okay, so at long last, let me write that down. We end up with our E2 page. It's sort of awkward to describe the middle stages, but when we get to E2, we've just done the right-derived functors for G to the right-derived functors for F of A. Okay, and this is really, that happened because this was a proper injective resolution. So that was really key here. Okay, well, now I have these two spectral sequences. On the one hand, I know the E infinity page because I just get this stuff. And on the other hand, I know an E2 page, and it has to have the same E infinity page. Okay, so these converge to the same thing. Not necessarily the same E infinity page, but the same associated graded of the same thing. And that associated graded had no extension problems whatsoever, so it really is the same thing. Well, okay, I should say that associated graded had no extension problems, so I really know what it converges to and associated graded of. It's possible that now on this version, I will end up with extension problems on the E infinity page. I just know that it's still going to be an associated graded of the thing this is an associated graded of, but I know precisely what that is. Okay, I think I'm getting all kinds of tripped up in my words, so it's probably about time to end this video. The upshot now is that we found that there is a spectral sequence, this other spectral sequence, the second one, that has right derived functor of G applied to right derived functor of F. Okay, so we take the right derived functor of G applied to the right derived functor of F, and this cooks up an associated graded of the same thing the other one does, which was the right derived functors applied to the composition. Okay, and so that's our Grothendieck spectral sequence. All right, let me say again sort of what was the tactic here. On the one hand, we knew a nice spectral sequence that collapsed, and so we knew the E infinity page. And on the other hand, we knew a spectral sequence that started, and by started I mean at the E2 page, with something we were interested in. And because these both converge to the same thing, that tells me this spectral sequence is going to converge to the right derived functors of the composition. So it's really kind of a slick maneuver to play these two spectral sequences off each other in this way. And not even just to say, oh, I see that there are going to be some zeros here, and so there have to be some zeros there or something. But no, I actually found out what it converged to by playing the other spectral sequence game. So I think that's kind of a neat argument. But in any case, I think this is about all I'm going to say about the Grothendieck spectral sequence. So we've seen some baby examples, we've seen a rough idea of the construction. It's really just coming up with that nice double complex and playing these two spectral sequences off each other. And this is, again, very commonly used in algebra and algebraic geometry. And so it's a good one to know. But again, it's a spectral sequence for a double complex, which comes from a spectral sequence for a filtration. And so at the end of the day, we're really going to think about these kinds of filtered things. Also, true confession, I'm a homotopy theorist, so I don't tend to think too much about these algebraic geometry applications, but we should hear about some nice ones in the presentations at the end of the term. All right, let me stop there, and we'll pick back up next time.